Okay, so this is exciting. We're getting into complexity classes. We're really starting to think about the material that is, at least some idea of the material that is at the research frontier in the theory of computation. One of the remarkable things about the class is that you can go from sort of nothing, from the definition of computation, all the way up to at least having some idea of what people who are currently thinking about the problems, what it is that they're thinking about. Okay, so complexity classes. Last time we talked about complexity classes, gave the definition. Complexity class is a collection of problems. We don't distinguish between problems and the associated languages all that much, so it's a collection of languages. Usually you'll have the collection determined by some particular complexity consideration. So maybe say you'll look at all problems that run in linear time, or maybe you'll look at all for which there's an algorithm that runs in linear time, forgive me. So, or maybe you'll look at all the problems for which there's an algorithm that runs in quadratic space, something like that. Okay, so that brings us to our first class, in some sense the sort of basis class, the key idea, a P. So a language decision problem is a member of P. Language decision problem is a member of P if there's an algorithm for it that on a deterministic Turing machine, our regular model, deterministic Turing machine, runs in polytime. And again, polytime is our interest as some kind of solvability. So just to give a couple of examples, P is very important in part because the ordinary problems that we usually think about in computing are in P. If you take an algorithms class, you open the book up and it will say, here's how to solve this problem quickly, here's how to solve this problem quickly, here's how to solve this problem. Those answers are all in P. So here are some problems, some languages whose decision problem is in P. So just to start in here, the language of correct sums. You get in a triple, you get in a bit string representation of a triple. You get in a triple with the property that here, A, B, C, and you're going to try to decide is A plus B equal to C. Okay, and a triple is in the language if A plus B equals C, and a triple is not in the language if A plus B doesn't equal C. If somebody gives you the triple 3, 4, 5, you'll say no, 3 plus 4 doesn't make 5. But if somebody gives you the triple 3, 4, 7, you'll say, yep, that's right, that's a member of L1. Can you check that? Can you answer the question, is sigma an element, is sigma equal to, come on, there we go, is sigma equal to ABC, an element of L1? Can you answer that question in polytime? Come on, of course you can answer that in polytime. You can check whether A plus B makes C in polytime, no matter if A is 23 digits long and B is 49 digits long. You can still check in polytime. In time polynomial and the length of the input. Now, of course, if A is 23 digits long, then you're getting a large input, but still, you can check that in polytime. Okay, what about second example? Come on. Darn this thing. There we go. Second example is the language of sorted strings. So somebody's going to give you a tuple containing a bunch of strings, where somebody's going to give you a string, so it's essentially a tuple containing a bunch of characters. Sorry, I misspoke. And your job is to check, are those characters in ascending order, in alphabetical order, in dictionary order. So, I think you could, given the tuple, you could answer yes or no. You could write an algorithm that answers yes or no. This string is indeed in sorted order, and I think you could write an algorithm that answered that question, solved that problem in polynomial time. I think you could. Language of correct matrix multiplications, L3. If somebody gave you sigma equals the triple, A comma B comma C, where A times B equals C, and then the three or more matrices, could you check in polynomial time, given a particular triple, could you answer yes or no? Could you write an algorithm that answers yes or no in polytime? Yeah, come on, I think so. I think big O of n cubed kind of stuff. And again, if somebody gives you very large matrices, will it take a long time? Yeah, it'll take a long time. But they gave you large matrices, so your input's large. Okay, so you're allowed a longer time then. What about the language of primes? L sub 4 is, they give you k many tally marks, k many ones, and you're asked yes or no is k prime. Could you solve that in polytime? Yeah, I think so. Yeah. Yeah, you could write an algorithm that took in k many ones and answered yes or no, k is prime, and your algorithm runs in polytime. Yeah, I think so. Yeah. What about the language of nodes with 5 neighbors? So that, I've deliberately picked one that's less familiar here. So you're given a pair, a graph and a vertex, and you have to answer yes or no. The vertex in the graph has exactly 5 neighbors. So can you write an algorithm? Can you write a program? Can you write an algorithm that takes in that pair, g comma v, and in polynomial time, in time polynomial in the length of g comma v, decides yes or no? V has 5 neighbors. Yeah, I think you could write. I think you could write that. It would decide yes or no, and it would run in polytime. Yes, I think so. So all of those problems, all those languages are an element of the class P. P is a collection of problems, and every one of those 5 is an element of that collection. So I think any problem that you think back from algorithms class that you were asked to implement, I think it's a member of polytime. Okay, so what we have here is some vague picture trying to show what's going on. So, whoops, put my pen down by accident. So I have a blob. In this blob are all problems, where a problem is a set of bit strings. Okay. So it's all problems. Some of those problems have an algorithm. For some of those problems, there is an associated algorithm that runs in polytime. For some of the problems, there is not an associated algorithm that runs in polytime. So what we have there is P. Now, for some problems, there's an algorithm that runs in log n time. Great, 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 great. That's still there. It doesn't have to be x squared. It can just be log n or log n or some even better answer. So down, all the way down, you might imagine here is problems that run in time, constant time, big O of 1. Problems that run in time, log n. Problems that run in time in linear time, in real time. Problems that run in quadratic time. And so all those problems are all shoved together in that collection. And the interest in that particular collection, again, is that when you take an algorithms book off the shelf, all those algorithms, all those problems that are being solved in there fall into that shaded area. So it's obviously of interest. We, of course, take polytime to be somehow acceptable. A couple of remarks here. So the effect of the model computation. So we are working with Turing machines. The definition says Turing machines. Different models of computation work at different speeds. So in particular, from all the way back when the course started, when we talked about working with Turing machines, I think a person sensibly would say, Turing machines are a pain in the neck to program, and they seem very slow. If you want to read in your data, you have to go all the way. It was really annoying. So maybe in this Turing machine model, a problem might not have a fast algorithm, but on a real computer, on a RAM model computer, it does have a fast algorithm. That's a reasonable thing. That's a reasonable question. Turns out the answer is that maybe was mistaken. Close analysis shows that Turing machines are slower than other models, often slower than other natural models, by a factor of n squared or n cubed. So if we have a problem for which there's a big O of n algorithm on a RAM model, then the Turing machine algorithm might be big O of n to the 4th. But it's still poly. So if you have a problem that's poly on a RAM model, it's still poly on a Turing machine. Problems that fall into the class P with one natural model, including Turing machines, also fall into the class P using other natural models. Okay, so that question about the speed of different models was a good one. I'm glad I posted it, but it turns out not close analysis shows that that's not actually perfectly, turns out not to be an issue for the kinds of models we are looking at. However, there's a possible counterexample to the contention about being an at most polytime delay between natural models of physically realizable devices. Under the quantum computing model, there are several problems that we know of that have polytime solutions on a quantum computer, but we don't know of a polytime solution on a natural non-quantum model on a Turing machine. So again, the example listed here is integer factorization. We know of an algorithm to factor integers that runs in polytime on a quantum model, but we don't know of a way to do it in polytime on a non-quantum, on a Turing machine. Now, whether quantum models will be practical, physically realizable devices, I think it's fair to call that still an open problem, although an awful lot of progress is being made. Also, conceivably, there are polytime solutions for integer factorization on a Turing machine. But still, it's a necessary adjunct to the second paragraph there, that it seems at least very possible that there will be physically realizable devices that show this gap. They can do some problems in polytime that a Turing machine cannot do in polytime. So although we don't have a definitive statement, I think it's worth remarking. Okay, to close, what's the big deal in P? We're going to spend, in what time is left in the course, we're going to spend it using P as kind of our touchstone, as kind of our baseline for a complexity class. So why is P? So what's the interest? So we're going to talk about P a lot. Here are some reasons why. First reason, the obvious reason, the natural reason, is that Cobham's thesis asserts that problems for which there is a polytime solution form a very important class. Okay. As mentioned on the prior slide, a problem is in P based on any familiar model if and only if it's in P based on any other familiar model, with the caution in the back of your mind that quantum machines may prove to be an example, may prove to be a counterexample. So we don't know, but that possibility seems at least in the air. And then the last. It's natural from a mathematical standpoint to want to be able to say this, that if two things are easy to compute, then any simple combination is easy to compute. So if you give me two functions that are easy to compute, that are polytime computable, say, if you give me two functions that are easy to compute, then we'd want that any combination of those two is also easy to compute, fast to compute. So just to try to be a little bit precise about exactly what we're talking about here. So if I take the language of F to be the collection of n comma f of n's. Technically, it's binary bit string representations of the pair n comma f of n. And L sub g is n comma g of n. So that is to say, I have a language way to describe these functions. Then, P is closed under function addition, function scalar multiplication, function subtraction, function multiplication, and function composition. P is also closed under language concatenation and Kleene star. So, it seems that any reasonable way to combine, any normal, any typical, any desirable way to combine these two also leaves you with something in P. If you have two functions f and g, and you compose them, f composed with g, f circle g, then if the f and g are in P, then f circle g is in P. Well, I mean, so it's starting to look like P is a natural class, a reasonable sort of marker at the bottom of that blob that I drew, a reasonable marker of what is kind of our touchstone. Okay. Okay, and when we come back next time, then we're going to talk about the next class will be NP. So we're getting into the material that people who are studying this area in research are thinking about today.